Howdy students! Now that you had a chance to look at circuits a little bit, we're now going to talk about ways that we can classify circuits, special terms that we can use for different types of circuits, etc., etc. So our three main goals. First of all, we're going to dive into this whole idea of a schematic diagram and talk about how to interpret it and translate between schematic diagrams and actual circuits. The second goal is to talk about open, closed, and short circuits, three different special terms that we have for circuits, and basically explain how they function, what causes them to work or what causes them not to work. And then our last goal is to look at two different ways that we can connect different circuit elements like resistors or lamps, etc. Those two ways are called series and parallel, so we'll talk about what the difference is between those two and the special characteristics of each one. Now, first of all, when I say a circuit, all I really mean is that there is somehow a complete path for our charges to move, as we know they want to, from a high potential area to a low potential area. Okay, this is why you always see circuits creating these full loops, because the idea is our battery has two sides, one side that's got a high potential and one side that's got a low potential. In order to get the current to push from one side of the battery to the other, we've obviously got to have a complete path to get from one side of the battery to the other. If we have a break anywhere, then that's a problem. Now we can represent this using a schematic diagram, because often it's difficult to actually draw in little battery packs and little light bulbs and stuff. So for those of us who are somewhat more visually, artistically challenged like myself, we have these schematic diagram symbols, which are much more simple to draw. So just a nice little catalog of different symbols that we use in a schematic diagram, common elements that we'll have in our circuits. First of all, a straight line just represents a wire that current can pass through. Pretty intuitive. If we see a straight line and then another line coming out of it, possibly with a dot right there, we know that there is a wire connection there. So we've got a place where the wire kind of diverges, and we've got one path that way and one path going the other way. Now, to represent a resistor, since resistors we can kind of think of as causing friction for our current to kind of prevent it from moving, and also that diverts electrical energy into thermal energy, we kind of draw it as this jagged little thing up and down like that. Okay, so it just goes up, down, up, down, up, down. So that's a resistor. Now, a particular type of resistor that we have, one particular element that tends to have a fairly high resistance, is a light bulb, and that's one that we are going to be using fairly often, let's face it, in this class, especially since that's sort of the whole point of the project. So to distinguish that a resistor is in particular a light bulb or a lamp, we just draw a circle around that same resistor symbol to indicate that there's a light bulb there. We can also represent that just with a squiggly line if we're feeling really lazy. To represent a battery, some sort of source of both a high and a low electric potential, we've got two parallel lines right here running perpendicular to the wire. We've got one line that's longer, that represents the high potential side, and one line that is shorter, that represents the low potential side. So we know that in this particular example, the current would be flowing out the left side and then back over into the right side of this battery. Last thing to talk about is a switch. A switch is represented by having basically these little dots here to indicate that there's some place where we can have a connection, and then we've got an open line sort of pointing off to nowhere to indicate that the switch is open, or it goes all the way through to indicate that the switch is closed. Alright, so let's practice kind of translating back and forth between a schematic diagram and a regular actual circuit. Okay, so here's our first schematic diagram to look at. Take a moment, look at all the different elements present in there. What you will hopefully notice is that we've got three different major elements connected by these straight lines representing wire. Down here we've got our battery, our voltage source. Here we've got a switch, and here we've got a light bulb. Okay, so to see this in real life, it looks like this picture right here. So we've got our battery down here at the bottom, wire goes all the way around and connects to a switch. In this particular case, you notice that the switch is open. So we've got an open switch there. Whoops, and I lost this guy. All right, so we've got an open switch, as you can see. That then connects all the way around using this wire to a light bulb or lamp, which then connects back through this wire to the other end of the battery. All right, so basically that's just represented by this guy right here. Now what you may have noticed is the light bulb didn't light up. Why not? Oh my goodness. Well, as many of you have already indicated that you just intuitively understand, this doesn't work because we don't have a complete pathway for the current to go through. Our current would want to go out this way, but let's face it, there's no low potential source over here, so there's nothing pulling the current down this way. There's nowhere for them to go. It's kind of just a dead end right here. We call this an open circuit. Okay, so anytime we've got any sort of break in between one end of our battery and the other so that we don't have a complete loop for the current to travel around, we've got an open circuit and it won't work. Now this next drawing, I hope you notice, is exactly the same, except, hey, we closed the switch. So that means it's going to look like, ta-da! So all I did was take the exact same thing, open, closed, open, closed. Man, I could entertain myself for days. That's kind of sad. All right, so once I close that switch, we see that we've got a closed circuit. There is now a complete path from the high potential end of the battery to the low potential end for our current to travel around. That causes the current to travel through the light bulb, thereby lighting it up. And it goes continues around there and to the low potential end of the battery. Now there's one more thing that I could do to this circuit, and it would be a bad thing. A bad thing. So what I've done here is this is the exact same circuit as before, although I've made it a little bit larger. But what you'll notice is that I've added one extra wire going this way. So otherwise it's exactly the same as before, where we've got the switch and then the light bulb and then down and back again. But here's what you're going to see. I'm going to go ahead and actually construct this for you guys, albeit not for long. Alright. So here's what you'll notice. Alright, I'm starting off with the same circuit as before, but now what I'm going to do is take this extra wire and add it in just around the battery. What happened to my light? It's gone. Ouch, and it burned me. Ha 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 ha. Why? Why did the light bulb go out? We left the switch closed. Why would suddenly adding this extra wire in there cause the light bulb to go out? Well, the reason is, as we've mentioned before, charges are kind of lazy. You know, they don't really want to have to go through the light bulb and face all that resistance and get slowed down. They want to just be on their way, get as quickly as possible from the high potential end to the low potential end. So when the current, there we go. When the current sees that there is this path right here that has no resistors on it whatsoever, it kind of goes, hey, I should just go through this way. Why should I bother getting slowed down through this light bulb if I can just go, you know, whip right through here with as little resistance as possible? Now, I'm sure the current would, if it had a brain, think that was great. We would not. What we have created there is a short circuit where we've got one path where the current can travel through with virtually zero resistance. And as we talked about last time in class, when we have a situation where there's very low resistance, that means a very, very high current. A high current enough that we get fire and all sorts of bad things, plus it drains the batteries, which makes me mad. So, yeah, short circuits, not so good. This is why also when you spill water on your laptop, for example, you can create a short circuit, which will cause sparks and fire and all sorts of wonderful things, because basically by putting the water onto the wiring of your computer, you have now created a new low resistance path for the current to travel through and mess up your computer in all sorts of delightful ways. So the next thing, the last thing that I want to talk to you about is how we can go about connecting multiple light bulbs to a single battery. Now, I'm just going to go ahead and construct that really quickly. Now, one example of how we can do this is shown in the schematic diagram right here. What I hope that you notice is that what we have is, why does that keep doing that? A battery located right here. Current will travel all the way through, and then we've got one light bulb right there, continues on, hits another light bulb, and then continues to pass through. Right? So we've got one complete loop with two light bulbs on it. I know you constructed this in class the other day. We call this a series connection. Okay. These two light bulbs are said to be connected in series, basically because the current has to travel through both of them in order to get from one end of the battery to the other in a series. Okay. Now when we construct that, we end up with, you can't see that, something that looks like this. So we've got the current traveling through this wire, through this light bulb, then through this wire, over to this light bulb, which then connects back again to our battery. Okay. Now what I hope you'll notice is that the lights are much dimmer than they were before. I mean, they're still giving off light, but it's not nearly as bright as it was previously. Right? Now, in this particular type of circuit, we only have one path for the current to go through. It doesn't really get any options here. It has to go around the loop. There's only one place for it to go. Okay. And since that same current has to go through everything, what we'll find is that if we measure the current across each of these lamps, it's going to be the same no matter what. So the rate at which charge is moving through our light bulbs is the same at every single point along this loop. It's not like it's going faster here and slower there. That wouldn't make any sense. It has to be going the same speed all the way through. What is different, however, is the voltage drop, the difference in potential from one side of the lamp to the other side. It's going to be actually split evenly between these two lamps. Okay. The drop in voltage is what causes our light bulbs to be so much dimmer, because whereas before, if we had just one bulb, we would have a total voltage of 3 volts. But now that we have two, we have to take that voltage of our battery and split it in half. That causes our light bulbs to be much less luminous. Now we have one other option that I think many of you will like. And it looks like this. Again, we've got two light bulbs connected here. But this time, instead of having just one path, we actually have two different paths. It's kind of like two different loops that our light bulbs are located on. I'm sorry, I'm trying to construct and talk at the same time. It is more than my little brain can handle. Here we go. One more wire. Almost there. All right. So here we are. Okay. Now this one's going to be a little bit harder to see in the limited amount of space that we have, but I will do my best. All right. So we've got, again, our battery pack. It's got a wire coming out from it, and then once we get to the end of that wire, we have two different places that the current can go. It can either go this way and travel through this light bulb, or it can go through this wire and travel through this light bulb. Okay, so we see that whereas before our current all had to go through one loop and pass through both light bulbs, this time the current gets a choice whether it wants to pass through this light bulb or pass through that light bulb. Now we call this type of connection a parallel connection because if you look, our two light bulbs are parallel with each other, just like parallel lines. Okay. Now, as I mentioned, there are now multiple paths for the current. The current will come along here from the battery, but then it gets split when it reaches this junction. It can either turn at that point or it can keep going straight. Okay, so our current is going to end up getting split as a result of that. Some current will go this way, some current will go that way. However, the voltage will still end up being the same for each device. So the voltage remains the same. The voltage here is the same as the voltage here, even though the current ended up getting split at this point. Okay, so that also explains why these light bulbs are so much brighter than the ones that we saw in the series connection, because they still maintain that full 3-volt potential difference from one side to the other. Now, it used to be that Christmas lights were all connected in series, so they were connected in something that looks like this. Now, what many of you notice is that if you have a connection like this, if you cause a break at any point, if you open up the circuit, all the light bulbs go out because we only had one path for them, and if that path gets ruined, none of the current can flow. This is why there's this whole running joke about how the most frustrating thing about Christmas is having to figure out which bulb it is that burned out that's causing the entire strand to not light up. Now what they've started doing more recently, is they've started connecting instead these Christmas lights in parallel with one another. And as many of you notice, the nice thing about that is that what happens is even if this bulb burns out and we end up losing this pathway, we still have another pathway that the current can travel through. So this light bulb still lights up even though this light bulb doesn't. So that makes it much easier to figure out which bulb has burned out and get it replaced. And even if you don't replace it, you still have all these other bulbs that are still nicely lit up. So those are two ways that we can connect multiple elements to the same battery. That's all the new information I have for you. So let's check out how we're doing. So a couple questions for you to consider. We've got a schematic diagram here for you to look at. First question is, what's going to happen in this diagram when the switch is closed? What's going to happen in that circuit? Second question is, considering this diagram, if we were to measure the, measure different aspects of these two resistors, this resistor here and this resistor here, we would find one thing in common between the two of them and one thing that is different between the two of them. So, what is that? Take a moment, think about it. All right, hope you're ready for the answers. Okay, so in our first question, what we would find is that if we close this switch, not only would our bulb cease to light up, we would have created a short circuit that could cause a fire. So basically by closing this switch, what we've done is we've created a very low resistance path, a virtually zero resistance path for the current to travel through. So when the current reaches this junction right here, all of it's going to travel through the closed switch, causing a very, very high current and all sorts of bad stuff. Okay? This is also why I think some of you accidentally created this very thing in the activity that we did recently. And what you ended up finding as a result was you had a situation where you would turn on your switch or you would close your switch and it would turn off the light. But if you open the switch, then the light shone brightly. So it looked something like this right here. So what I've done is I've actually shorted out my own circuit. Okay, I've created this pathway here where the current can just travel through the switch. Now as long as the switch is open, our light bulb lights up, but as soon as I close it, we start diverting current away from the light bulb. but if I open it again, light bulb lights up. Pretty weird. All right. As for the second question for you to consider, in this situation, we've got a parallel connection between our two elements here. So whenever we have two resistors in parallel, we know that they're going to have the same voltage, same potential difference between the two sides of them. So maybe if we lose 3 volts here across resistor 1, we also lose 3 volts here across resistor 2. However, the current is going to be split between them depending on the actual resistance values of each of these. Whichever one has the higher resistance, that one's going to have a lower current, and whichever one has the lower resistance, that one's going to have the higher current. I know this was kind of a tricky one to take in without being able to ask questions, so by all means, keep those burning inquiries in mind, and we will talk about them in class. Have a good day.